Hi, my name is Simon, and I will be presenting our work on implicit latent variable model for scene-consistent motion forecasting. In a traditional self-driving pipeline, prediction, or motion forecasting come after detection and tracking the objects around a self-driving vehicle. Prediction is a challenging task for three main reasons. First, the future is inherently uncertain, and in order for the self-driving car to navigate safely in complex traffic, we need to take into account all plausible futures. Secondly, the distribution over future trajectories is highly multimodal. As shown in the illustration, a vehicle may choose one of the two branching lanes. And lastly, actors interact with each other, and we must take this into account when we model the future. So far, most of the work in motion forecasting for self-driving has focused on independent actor predictions. In particular, works characterize the marginal distribution over actors instead of the joint distribution. This has the benefit of simplicity and allow us to quickly generate trajectory samples in parallel, and it gives us an estimate of the expected free space that a self-driving vehicle can use. This assumption, however, means that we do not capture the dependency between future trajectories across actors. Since the output distribution for each actor are independent, when we sample from each of them, we might obtain inconsistent futures like the illustrated case where there's a collision. Thus, it doesn't allow us to look at the separate realization of future scenes as a whole. This brings us to the main focus of our work, to model the joint distribution over actor future trajectories. If we can do this, we can obtain distinct samples of the scene that represent separate realization of the future. The trajectories will be socially consistent across actors, as the two examples shown here. This will enable motion planning research to reason about how to react to multiple predicted scenarios, as well as provide smart agents for simulation. Since in a simulated world, we need to capture the dependency across actor behaviors. One most recent approach to model future interaction between the actor is via joint autoregressive formulation. At each time step, we can condition on the previous predicted waypoints of the actor and other interacting neighbors. This also allows us to make counterfactual predictions by asking what would the actor do if another actor stopped in this way. While expressive, this approach requires slow autoregressive sampling that's not amenable to the real-time requirements in self-driving. Furthermore, there's the issue of compounding error. This is because there's a gap between training and test, where training, the prediction is conditioned on ground truth's previous waypoints, but at test time, it's conditioned on waypoints sampled from model. Furthermore, these methods generally assume a perfect perception setting in which the input of the model is the true past state of the world. Now, in contrast, we work with a much more challenging setting where we aim to reproduce motion forecasts directly from sensor data and high-definition map. This means that we have to learn a joint perception and prediction model. To do so, we first extract features from LiDAR and map with a backbone CNN. Once we have the rich features from the whole scene, we can obtain object detections, which is shown in red here. Since we know the information that's ahead and to the side is the most relevant, we attribute this region of interest to the actor, and then we can pull the features on that region as a summary of the actor characteristics. We can now further process these features using the CNN with global pooling and obtain a feature vector for each actor, which is passed to the prediction model. Now, to tackle the issue with the social autoregressive formulations, we propose a latent variable model that features parallel sampling of trajectories. The key idea here is to have a scene latent variable responsible for capturing the unobserved scene dynamics. In fact, we make this latent variable flexible and continuous and make sure that it captures all stochasticity in the scene. The challenge, though, is that there are a variable number of actors in each scenario, and they all have different map topology and traffic situations. This makes learning a single latent space particularly challenging. To ease learning, we adopt a distributed representation of the scene latent variable where the partitions are spatially anchored to the actor. This design allows the latent space to scale to scenarios with any number of actors. In particular, we introduce a novel graph neural network-based scene interaction module to encode and decode from this latent space. Before we go into the detail of the modules, let's summarize the high-level inference procedure of our model. Starting with the extracted actor features, we used a prior module to infer a distribution over the scene latent variable Z. Then, we can sample from this distribution and pass the sample through a deterministic decoder to produce one realization of the future. We can then sample again to obtain a different future. Although I've illustrated the sampling process as sequential, for clarity, the sampling process is in parallel since there are no dependency between different samples. Let's take a deeper look into the scene interaction module to understand how it works. To encode the spatial relationship between the actors in the scene, we use a spatially aware graph neural network to implement our scene interaction module. In our case, each node in the directed graph corresponds to an actor. The graph processing has 4 steps. First, we initialize the node state with ROI pooled features and spatial information such as the location, dimension, and heading of the vehicle. Based on the spatial information, each actor has its own coordinate system defined by the centroid and its heading. The message function is parameterized by an MLP that's shared across edges, and experimentally, we found that transforming the spatial information of the sender node into the receiver's coordinate frame is important. We use max pooling across neighbors as our permutational invariant aggregation function. And we update the node state with a GRU cell, where the previous node features are used as hidden states and the aggregated message as the inputs. Our model is fully differentiable and can be trained end-to-end through backpropagation using a multi-task objective. We apply cross-entropy loss to the detection scores and a smooth L1 loss to the bounding box regression targets. Here, we show the gradient flow in the dashed red arrows. To jointly learn our prediction module, we follow the conditional variational encoder framework and introduce an additional encoder module that has access to ground truth future. The learning objective consists of a KL loss that penalizes the divergence between the prior and encoder network, and finally, a reconstruction loss of the decoded trajectories. Before moving on to the quantitative results, let's take a look at some samples from our model. Here, we investigate the properties of the latent space by interpolating between the latents of distinct output samples from our model. On the top left, we can see turning versus going straight behavior with smooth transitions. In the top right, we can see a complex three-way interaction, where the 2 vehicles in the row predict turning or slow-moving trajectories, and the third vehicle pulls out of the driveway. And when the 2 vehicles in the row keep constant velocity to go straight, the vehicles in the driveway yields. On the bottom left, we can see how the speed of 2 cars that follow each other vary consistently. And finally, in the bottom right, we can see all the range of possibilities from a left turn to a U-turn. Now, to measure the performance of our model for scene-consistent motion forecasting, we propose 2 new scene-level metrics that measure the quality of trajectory samples jointly over all actors. First, we define the scene collision rate as the percentage of trajectory samples that collide in a given scene. Then, we extend the commonly known actor-level distance metrics to the scene-level distance metrics by taking the minimum and average over scene samples instead of actor samples. To see this, consider this left-turning scenario where 2 vehicles negotiate. A model that produced the predictions 1 and 2 here scores well on the actor-level minimum FDE metrics despite not being socially consistent. Our scene-level metric correctly selects prediction 3 as the most consistent sample for evaluation. Our method outperforms all previous methods by a big margin in 2 large-scale self-driving datasets, ATG4D and new scenes. Most notably, in ATG4D, our method achieves 75% less collision amongst motion forecasting a scene sample than any previous proposed method, including the social autoregressive methods that in theory can characterize the joint distribution over actor trajectories. Let's look at how the samples from our model compare to the baselines. In the first 2 rows, we show multipath and ESP. For both cases, the 2 most different scene samples out of 50 capture very low-level variations at the actor level corresponding to different goals or speed profiles, but with a single general mode at the interplay between the 2 vehicles facing the intersection. On the contrary, our model identifies that there's an interaction between the 2 vehicles at an intersection, and that one on the left can yield to the one on the right or vice versa. Now, in this video, we sample 50 scenes from our model and aggregate them using transparency to show the characterization of marginal distributions. Quite surprisingly for us, our model not only achieves scene-consistent samples, but also a better understanding of the map compared to the baselines. Finally, we put our model in the broader context of self-driving system to understand how it influences the safety and comfort of the SDV's planned trajectory. In order to do this, we use a state-of-the-art motion planner and pass in 50 samples to the scene to characterize the obstacle. We show that our model results in safer and more comfortable motion planning. We achieve this performance gain despite the planner only reason about actor independently and then not at the scene level. So, in conclusion, we introduced an implicit latent variable model that produced inconsistent motion forecasts directly from sensor data. Our model produced more realistic trajectories with better map understanding. And finally, it improves system level metrics and results in safer and more comfortable rides.